Have you ever wondered if we could power an entire city with something as simple as a special ceramic powder? I know, it sounds like something straight out of a sci-fi movie, but it's the real idea behind a technology called the fuel cell. Today, we're going to dive into how one scientist's mission to solve one really stubborn problem might just unlock a whole new chapter for clean energy.
So, let's start with that big question. What if? This is really at the heart of our story today. And the answer, it turns out, isn't about discovering some crazy new element. Nope, it's about finding a much, much cleverer way to use materials we already have, all to build a better engine for the future.
Okay, so the piece of tech we're talking about is the solid oxide fuel cell, or SOFC for short. The easiest way to think about it is like a super efficient battery that never ever dies, as long as you keep feeding it fuel. It can run on hydrogen, natural gas, you name it. It's an incredible concept, but it's got one huge, and I mean very hot problem.
And that brings us right to the main challenge. See, the reason these amazing devices aren't powering everything around us is because they have to run at incredibly high temperatures, and that heat creates a whole cascade of engineering nightmares. Let's break this down. On the left, you've got today's fuel cells. They have to run at a blistering 800 to 1,000 degrees Celsius. That's so hot you're forced to use really expensive, exotic materials. The dream, the goal, is what you see on the right. Get that temperature down to a more manageable 500 to 700 degrees. Just that one change would mean we could use cheaper stuff like steel, the whole system would be more reliable, and it would be way more flexible.
And this quote from the research really just hits the nail on the head. This isn't just about getting something to work in a lab. It's about making it practical, making it affordable enough for the real world. The idea that you could use plain old steel instead of some high-tech ceramic, that is the key that could unlock this technology for everyone.
So, if you have a temperature problem, where do you start? Well, you go on a hunt for a new material, a kind of secret ingredient that can do its job at a lower heat and hopefully change the whole game.
And here it is. The hero of our story is a ceramic called gadolinium-doped ceria, or GDC. Scientists figured out that this stuff was an absolute superstar at moving oxygen ions around, which is the most important job inside a fuel cell. And the best part? It could do it at those much cooler intermediate temperatures. This was, potentially the big breakthrough they were all searching for.
But just finding the right material isn't enough, right? You need the perfect recipe. So the first job for the researcher, M.G. Chourashiya, was to figure out the exact amount of gadolinium to mix in. After a ton of tests, he landed on 10% as the sweet spot. But there was a problem. When he tried to make this stuff in a solid brick, or a bulk form, he kept getting these nasty impurities that just gummed up the whole works.
Okay, so what you're looking at here is basically a chemical fingerprint, and it's showing us that exact problem. Those big, sharp peaks, that's the GDC material we want. But you see that little extra peak marked with a star? That's an impurity. It's like a tiny roadblock for those oxygen ions we need to move. This was the big hurdle that proved the old-school bulk method just wasn't going to cut it. He needed a new plan.
Now, faced with this challenge, Chourashiya didn't just try to tweak the old method. He went for a completely different and, honestly, a much more elegant approach. The idea was to build the perfect material from the ground up, not as a solid chunk, but as an incredibly thin, perfect film.
And that method is called spray pyrolysis. The best way to picture it is like an atomic-level 3D printer. Instead of mashing powders together, you dissolve your ingredients into a liquid, you spray it as a superfine mist onto a hot surface, and you let chemistry build you a flawless, densely packed layer.
Let's just walk through this because it's really cool. First, you mix up your chemical cocktail, then you turn that liquid into a fine mist. Step 3, you spray that mist onto your foundation, which is already heated up. The second those tiny droplets hit that hot surface, boom, they instantly react and lay down a perfect layer of solid GDC. And for the final step, you bake the whole thing. It's a process called annealing, and that locks everything into a super dense, totally flawless film.
So the theory was brilliant. The method was really elegant. But the only thing that matters is, did it actually work? It was time to put this brand new film under the microscope and see if the results matched the promise.
And the answer was a huge, resounding yes. I mean, just look at this. On the left, that's the rough, kind of porous ceramic base they started with. And on the right, that's the GDC film made with spray pyrolysis. It's unbelievably smooth, it's dense, it's perfectly bonded. It is a total night and day transformation from a rough foundation to a piece of beautiful, high-performance engineering.
The numbers behind the picture are even more impressive. The film was just 13 micrometers thick. That's thinner than a human hair. It was over 96% dense, which is absolutely critical, because you can't have fuel leaking through. And it made a perfect, gas-tight seal with the layer underneath it. For fuel cell engineers, these are basically dream specs.
But here it is, the ultimate test. How did it perform? This graph shows us the electrical conductivity. See that line plunging down at the bottom? The one labeled GDC pellet? That's the original bulk material, the one full of impurities. Its performance is, well, terrible. Now look at those lines way up at the top. Those are the thin films from the spray pyrolysis. They are literally thousands of times more conductive. It is the difference between a bumpy dirt road and a 6-lane superhighway for those oxygen ions.
And this all comes down to one single number, 0.1 Siemens per centimeter. Now that's the measurement for conductivity, and it was the golden target everyone in the field was aiming for. And at 500 degrees Celsius, Chourashiya's thin film hit that target dead on. Mission accomplished.
You know, hitting a number in a lab is one thing, but the real excitement is about what a success like this actually means for the future. This wasn't just some academic exercise. It was a really critical stepping stone towards a whole new generation of energy. So let's boil it down. What this work did was prove that this clever spray technique is a fantastic way to create the high-performance heart of a fuel cell. It hit the magic number needed to make these intermediate temperature fuel cells a real possibility. And that is a huge step toward making fuel cells that are cheaper to build, that last longer, and are just way more practical to use. And you can really hear the ultimate goal in the researchers' own words. This was never just about the science. It was about taking this incredible technology and getting it out of the lab and into the real world to help it become a commercial reality. So this amazing research perfected the heart of the fuel cell, that electrolyte layer. But that's still just one piece of a much bigger puzzle. The next giant leap is to get all the other parts of the fuel cell working just as well at these new, cooler temperatures. This work has truly paved the way, though, bringing us one massive step closer to a future that could be powered by clean, cheap, and super efficient energy, all starting maybe from a simple ceramic powder.